Hello and welcome back. This is the sixth video in the series of learning physics. I believe you had a break in terms of a first term examination and hopefully you did well. And my intention is really to restart the series of videos that are suspended for some time, probably because of the term that was intervening. But now I also want to make a transition from matter to energy. The first four videos that I presented were essentially on matter, which is solids, liquids, and gases. We spoke about the intermolecular forces. We spoke about the change in states of matter, like ice melting into water and vaporizing into steam. And we also spoke about density of matter. In the very short fifth video, I simply related matter and energy through a relationship called E is equal to mc square, where E is energy, m is mass, which is a significant part of what matter is defined as, and c square, which is the square of the speed of light. And I did mention that it's almost impossible to figure out why it is so with the amount of physics that you know of today. And in fact, we will need relativistic mechanics to understand that relationship. So that apart, let's now progress with the next set of videos, maybe 3 or 4, which cover energy. Now, energy is something that's not new. We use it very, very regularly in our day-to-day life. You often get up in the morning saying, I just don't have the energy to get up. We also say, I just don't have the energy to go and play a sport. What do you mean by the word energy? If you were to even think of just as a word of English rather than of physics, if you have energy, you can do something, right? You have the energy to play. You have the energy to dance. Essentially, you have the energy to do some work. And that work can be dance or play. So in some sense, energy is our ability to do work. And in physics, energy is as much a concept in physics as is work. We define work in a system as the amount of energy that we would put in to do a certain amount of work when a body is displaced by a distance through a force acting on it. So in some sense, the work done is the product of the force acting on the body and the displacement that it causes on the body. So you can call it F dot S, where F is the force, S is the displacement. And I use the word displacement rather than the word distance because in physics, displacement is about the distance covered by the body between a state and its next state. And for example, if you started from somewhere and came back to the same place, while you covered some distance, the displacement is zero because essentially nothing has changed the configuration of the body from where it started and where it ended. And therefore the work done can be zero. Which is a little bit funny because if you're running around in circles and coming back to the same place, you would think that you've done some work. But in physics, the way it's defined is it's the displacement that matters because essentially the system has to change. And therefore it's not distance and therefore it's displacement. So in some sense, energy is the potential of the body to do work. And therefore work and energy are very equivalent. We also define energy as having two types of energy. The energy of being in rest, which is called potential energy, and the energy while something is in motion, which is called kinetic energy. In some sense, when you do work, you are converting potential energy into kinetic energy. Kinetic energy while the body is moving, but potential energy when the body was at rest because it has the potential to convert that energy from potential to kinetic energy. So in some sense, whether it is work done, whether it is potential energy or whether it's kinetic energy, you can see that it's just moving between those three things. And that comes from a very, very fundamental understanding in physics where it says that energy can neither be created nor destroyed, which essentially means it can't be created and can't be destroyed, but it's getting used. The only way you can think about its energy is getting transformed. So in some sense, potential energy and kinetic energy are similar, except that something is transferring between potential and kinetic energy. So in some sense, potential energy is the energy the body contains by virtue of being at a certain position, whereas kinetic energy is the energy that contains because the body is in a state of motion. Let's think of it as some other way. Let's think of a ball or a stone or maybe even yourself, which is at the foot of a hill. Now I do something that I carry the ball or the stone, or you carry yourself up to the mountain. You've obviously done work because you are elevating your position from here to there, and you know that you get tired, which means you've done some work. But I said energy can neither be created nor destroyed. So where is that energy going? It must be getting stored somewhere. That's how we define potential. So the potential energy of the body at the base of the hill is very low, but as you climb up, you are kind of getting kinetic, and the kinetic energy or the work done is getting used to kind of increase your potential energy. So therefore you can see that in this whole system, between you being at the bottom of the mountain and going to the top of the mountain, you essentially changed your potential energy by doing work on yourself in climbing up that hill or mountain. And there's nothing absolute about energy, so you just have to define a state. So for example, if at the bottom of the hill you assume that whatever energy you had is zero, when you do climb up the hill, your potential energy has simply gone up by your mass multiplied by g, which is your weight in total, which is mass into g, which is called an acceleration due to gravity, and the height to which you are coming. It's not really the distance of incline that you climb, it's simply the absolute height that you climb, and that's your increase in potential energy. Therefore, as you can see, it takes energy to take the ball or roll the ball up the mountain. But you also realize when you're at the top of the mountain, you simply leave the ball there, it's going to automatically roll down that mountain. That's because all the potential energy that you increased in taking it up the hill will automatically allow the ball to roll down the hill, and its potential energy will come back to the same that it started with, which is, let's say, zero. And therefore the work done then to come down is also conserved, because it's just the potential energy, which was mgh at the top of the mountain, has now become zero when it comes back to the bottom of the mountain. So the work done in translating the ball from the bottom of the mountain to the top is done by you. You are kind of moving it up and therefore increasing its potential energy. But on its way back, it just uses its potential energy to bring it back down. So in some sense, you can see that law of conservation of energy is pretty much valid here. You raised its potential energy by doing work, by giving it kinetic energy, and then it came back and used its potential energy to give itself kinetic energy to come back to the bottom of the hill or mountain. There are lots of nice videos of inclined planes and ball bearings going up and down through curved. When just look at it in YouTube, you'll understand the concept of how potential energy and kinetic energy kind of move around. That's not the only case though. You can see it everywhere else, that kinetic energy is getting converted into potential energy and vice versa. It's true with springs. When you push a spring in, you are kind of enhancing the potential energy of the spring by compressing it. And when you leave it, the spring jumps back and uses that potential energy to kick back and move the whatever is pressing back. So that's how a spring kind of stores energy in and then releases energy, and that change is the potential energy that the spring retains when it is compressed, or same when it's expanded. So its rest position is this. You pull it away, you see that it will come back because it's kind of yo-yoing between its kinetic and potential energies. Most of the systems that we spoke about are mechanical systems, or what we see around us, what we call classical mechanics. So, a ball rolling up a hill, a ball rolling down a hill, a spring. There are so many mechanical things. But remember, energy is not just about mechanical energy. You turn on a torch, you see light. Light is another form of energy. I'm speaking to you. I'm kind of straining my vocal cords, and there is this sound that is coming out. Sound is another type of energy. There's electricity, which is another kind of energy. There is wind which is moving, which is kinetics, but can then turn a windmill, which can then generate electricity, which can be again used to light a bulb, which is light energy. So in all of these cases, you see a myriad number of ways in which energy is just getting transformed. It's neither getting created nor getting destroyed. It's simply getting transformed from one type of energy to the other. So in some sense, that's the simplest way to understand what energy is all about. The easiest way to understand energy is to simply sit somewhere and look at everything that's happening around you. Every movement, even the stillness. And if you see something happening, just imagine what must be the energy cycle that must be going on, transforming to give you what it is. For example, look at a mobile phone. You have a battery inside which are chemicals, and those chemicals react with each other and kind of get consumed, and in that process the chemical energy that is stored in those chemicals and the reaction is coming out and giving you some electrons which move around in a wire to give you some current, which can then pass through an LED, which is essentially a smallest element of your display, which is then glowing and providing light energy. And that light energy is then absorbed by your retina, and that kind of produces some other charges inside your brain to make a perception of what that image is. So in some sense, energy is just transforming into various forms, starting from chemical energy into electrical energy into light energy, which on your eyes again becomes electrical energy, and then it kind of provides a sensation. So in some sense, energy in all of this is just getting transformed, and it can never really stop. So I think the understanding that you really need to have is that if I now figure out that energy is universal, the law of physics of saying conservation of energy, which is energy can neither be created nor destroyed, is true, then the rest 3 or 4 videos are all going to be about this transformation of energy in different aspects. So today we talked mostly about mechanical energy, and the reason we introduce energy through mechanical energy is because that's something that you can see it intuitively around you, and it's very simple. And right from childhood, when you see a ball rolling, or when a child learns to walk, you begin to interact with mechanics or mechanical objects, and that's how mechanics was among, and it's called classical mechanics for that reason. So I think that's where I will stop today. I've been speaking for the last 14 minutes, but I guess you get a sense that we are going to cover this journey, starting with, of course, mechanical energy and introducing the concept of kinetics and potential energy. But we will go on to see how this energy manifests itself in each of those forms, and in each of those forms, what are really the ways in which we can talk about energy. So for example, here we talk about half mv square, as the kinetic energy is half into mass into velocity square, so that's kinetic energy. mgh is the potential energy because of a gravitational field. But in other cases, like electrical energy, you'll realize that potential energy is defined by some other values in that context, and that kinetic energy also may be defined differently. So with that, I let you take the next few minutes to think about what I said, and I look forward to seeing you again in a week or so to come, where we'll talk more about the nuances of energy. I hope at some point we will keep talking about energy and its relationship with matter. If you haven't figured out, if you just go back and look at the matter, we talked about heat energy, we talked about pressure, all of those are actually energies interacting with matter. Pressure is actually just mechanical energy of molecules hitting the wall of a container, like we said. That was just mechanical energy converting as pressure, which kind of was an inherent property of matter. So was, by the by, heat energy, which we didn't speak about today. But heat energy is a very, very important form of energy, because heat energy then drives the temperature of the body, making it go from ice, which is below 0 degrees centigrade, to water between 0 and 100 degrees centigrades, and to steam above 100 degrees centigrade. So therefore you see that already you are beginning to think that there is a relationship between matter and energy, not in terms of an equivalence of E is equal to mc square, like I said, but in terms of the interaction of matter with energy. See you then.